the chemical and physical properties of any substance are related with the relative disposition of the atoms, ions, or molecules in that substance. Therefore, one of the fundamental aims in chemistry is determining the exact location of the atoms in order to get information about the bond lengths, bond angles, non-covalent interactions, of any other properties of interest. This allows us to unequivocally identify a newly synthesized compound, understand its formation, and understand the properties that made us prepare the material. But how can we obtain the exact location of the atoms? In principle, in order to obtain the geometrical parameters of a molecule, we could think of using a microscope in order to see the molecules. But this would mean using a wavelength enough to resolve between the distance of an atoms, which are of the order of magnitudes of angstroms. This means using X-rays as the source. And at the moment, it's not possible to have lenses that can focus X-rays. We need to use an alternative approach, and we can use diffraction methods for that. When the X-rays encounter an atom, a phenomenon called elastic scattering is produced by the electrons. The incoming X-rays are absorbed by the electrons, but then are released in the form of new X-rays of the same energy as the incoming. Interference occurs when X-rays interact with each other. If the waves are out of alignment, the signal is cancelled. This is called destructive interference. If the waves are aligned, the signal is amplified. This is called constructive interference. Thus, a strong amplification of the emitted signal occurs at specific angles, where the scattered waves constructively interfere. This is called diffraction. In order to constructive interference to occur, the scattered waves must be aligned, meaning that the second wave must travel a whole number of wavelengths. With simple maths, it can be seen that this occurs at specific angles theta. From this, we can derive an important equation commonly known as Bragg's law, named after Sir William Henry and William Lawrence Bragg, father and son, who won the Nobel Prize in 1915 for their work analyzing crystal structures with X-ray diffraction. Bragg also showed that a crystal can be regarded geometrically as formed by a set of parallel planes, each of them with a different spacing and thus fulfilling the equation at different angle theta. What we need to perform a diffraction experiment is a crystalline solid material, made up of a large number of identical molecules which are arranged in a precisely regular way, repeated in all directions, to give a highly ordered structure. Depending on the size of the particles, we can differentiate between single crystal and polycrystalline powders. Single crystals are large crystals, and by large, we mean sizes of 0.1, 0.2 millimeters. The crystals are first analyzed with a microscope, which allows us to evaluate the quality by looking at the shapes and faces. An important feature of a microscope is to have polarized light. In that case, the crystal can be evaluated by looking how it extinguishes the polarized light at certain angles. Once a suitable crystal is found, it is transferred to the goniometer of an X-ray diffractometer. In a single crystal X-ray diffraction experiment, a crystal is placed in the center of the instrument. The crystal constantly rotates in the beam of X-rays, and the 2D detector records the signal from the sample. The X-rays are generated in an X-ray tube, and the wavelength depends on the nature of the metal anode. In this case, we have molybdenum radiation, which means a wavelength of approximately 0.7 angstrom. The incident beam illuminates the crystal, which is placed at the center of the instrument at the goniometer, and the diffracted X-rays are collected by a CCD detector. The experiments are typically carried out at low temperature, as this improves the signal. The mathematical relationship between the arrangement of atoms in the crystal structure and the intensities of the diffraction pattern is the Fourier transformation. Thus, it is possible to obtain a crystal structure through this well-known and well-established mathematical operation. The diffraction pattern is the Fourier transform of the length of the electron density, and the electron density is the reverse Fourier transform of the diffraction pattern. Then, from the position and the intensity of this signal, the 3D structure of the sample can be unambiguously determined. However, despite the high power of this technique, single crystal diffraction has an important drawback. The structure that we have determined corresponds only to the single crystal that we have measured. How can we overcome this? By using X-ray powder diffraction, which is a technique that measures materials in bulk. A powder diffractogram is like the fingerprint of a material. It is unique and specific for it. With this, we can confirm the structure we have determined through single crystal diffraction is representative of the bulk. X-ray powder diffraction can be measured with different setups. An important mode, because it uses a small quantity of material, is using capillaries. Once the capillary is loaded and centered, the diffraction experiment is analogous to that of single crystal diffraction. The beam illuminates the powder, and the signal is recorded by a detector which moves along 2 theta. X-ray diffraction has played a fundamental role in research in the last 100 years. Crystallography is a multidisciplinary field that links together frontier research fields and has played an important role, directly or indirectly, in numerous researchers that have been awarded Nobel Prizes. This includes over 40 different Nobel Prize awards and 53 Nobel laureates.